Hey everyone, welcome to Bite Size Buhl. My name is Mike.
And I'm Gavin.
And we are here coming to you from the Buhl Planetarium at Carnegie Science Center. This week we are celebrating the science of volcanoes. And we invite you to come on down and check out the Buhl Planetarium in person. We've got a brand new show titled Space Volcanoes. In our Rango's Giant Cinema, we have a documentary called Volcanoes, which is awesome, and even Pompeii the exhibition, where you can step back in time and learn about this ancient Roman city that was destroyed by Mount Vesuvius, but also preserved for archaeologists, and step back in time and learn about ancient Roman culture. Today, we are going on a tour of volcanic hotspots on Earth and
on Mars.
So we are giving you a little sneak peek at the inside of Earth to get things started. And you can see our core, our molten core in the center. Around the circumference of your view, you can see the crust, but we're mostly interested right now in the area in the middle. It's known as the mantle, and that's the mostly solid bulk of Earth's interior. It lies between Earth's super hot core and our thin outer crust. Now, Earth's mantle is about 1,800 miles thick. It's made of mostly silicates, so compounds made of silicon and oxygen, lots of magnesium oxide too, and other stuff. And it's mostly solid rock, but it's less solid, it's less viscous at tectonic plate boundaries. We talked about those last week. That's one place you can find volcanoes. And also, it's less viscous where places we call mantle plumes. In some spots, the mantle gets soft. It's able to move more plastically over the course of millions of years. And the transfer of heat and material in the mantle really helps to shape the landscape of the Earth. And one way it does that is through hotspots.
Hotspots are regions deep in Earth's mantle where heat rises through the process of convection. This heat creates melted rock, and melted rock, which is known as magma, pushes through Earth's crust and onto the surface to form volcanoes. Hotspots, magma plumes are also create hotspots as well. It's the upwelling of this magma through the Earth's crust.
Yeah, so last week we talked a little bit about how Earth has tectonic plates and volcanoes can form over those areas where the plates bump together. But as you just said, we can have these plumes of hot material coming out of the magma that form hotspots, completely independent of where plates are coming together. It's just a different way that volcanoes can form on the surface of the Earth. It doesn't occur at the boundaries of those tectonic plates. So we're going to dive in today to learn about some of these volcanoes that form because of hotspots. And to do that, first we are going to put the lid back on Earth, as it were. So we're going to reset for a moment. I'm using a software called Digistar 7. This is the same stuff we use to take a spin in Buhl Planetarium on site. And I'm going to turn the sky back on for everybody watching at home. Now we're going to fly back out into space. So hang on for a moment. We're going to head back out for a view of our beautiful blue marble from space. Gonna fly out just a little bit farther. And we're gonna take a tour of some volcanic hotspots. So as we head back out into orbit, Gavin, your pick. Which volcanic hotspot do you want to visit first?
We can start Yellowstone.
All right.
So, Yellowstone is actually a underground supervolcano, and supervolcanoes are volcanoes that, when they erupt, they could erupt so massively that it affects the whole global climate. A spot we're going to stop at real quick is the Grand Prismatic Spring. So, because of these hotspots, we have a lot of springs and geysers that form in Yellowstone, and one of the spots is a Grand Prismatic Spring, which is a lake that is it's like more like a pond that is extremely hot and full of different types of acids. And though it seems like nothing can live in it, there are actually creatures called thermophiles or extremophiles that can live in these extreme temperatures and environments. They actually give the lake its color, which we'll see in a second. And right in the middle, you'll see a dark blue, which is the hottest part of the lake. And the different colors of the lake are caused by these thermophiles in it.
All right, there. It's like we've landed on another planet, basically, now, right?
Yeah.
So, yeah, as you were saying, we've got those thermophiles, things that live in extreme heat, and they form a cool rainbow, really, a cool prism there, because as we get out toward the edges, it gets cooler, and different species can tolerate different temperatures, and that's why you see those different species forming those rainbow rings. I think the center blue is really interesting, too.
Yeah, and though it is difficult to see, in person, the lake itself is actually a rainbow color. It is every color of the rainbow.
Now, the blue in the center, there's actually no thermophiles right there. That's the color of water. Now, if you pour out a glass of water at home, you're not going to see the true blue color of water that's reflected by water molecules. But obviously, from space, we could see the blue of the ocean. The Grand Prismatic Spring being so deep, we can actually see it's essentially one big, long, deep column of water, and we can see the true blue color of water there, which I think is pretty cool. All right, we'll go ahead and start zooming out here. So the Yellowstone hotspot has produced lots of volcanic features. The Yellowstone caldera that you mentioned, that's one of the youngest. And this is something that's developed right under the North American continent. We're going to come back out to space. We're going to leave North America behind and come on up over to Europe. I'm going to move the sun just a little bit. All right, on your screens, you'll see a few islands right now. We're in the North Atlantic Ocean. You might be able to see Greenland up in the upper left, just the tip of Greenland. Ireland and England down to the lower right. Right in the center of your view is Iceland. And Iceland spans the Mid-Atlantic Ridge. What's that? Well, that's the boundary between two tectonic plates. If you think of Earth as kind of a cracked eggshell, the crust of the Earth, you've got these slow-moving bumper cars, these big slabs of solid rock that are moving over that hot mantle that we looked at earlier. Well, there's not just one uniform piece of rock, and where two of them come together, they sort of bumper car each other. We've got the North American plate and the Eurasian plate. In this case, those two plates are actually spreading farther apart year by year, about the same speed your fingernails grow. And as they're spreading apart, well, that allows new volcanic material to start building up crust in that region. That line you're looking at there, we call the Mid-Atlantic Ridge. Now, there's actually a cool coincidence here that makes Iceland very volcanic. It's sitting on a plate boundary. It's also got a mantle plume.
All of Iceland is actually a volcanic island that has formed for a long time now. And Iceland has multiple volcanoes on it, and it has erupted about a third of Earth's basaltic lava, which is lava that is very rich in iron and magnesium.
That's an amazing island to visit. So what we're looking at here is a volcano. It's actually covered by a glacier. Its name is Eyjafjallajökull. It's the mountain of the glacier of the island, and in 2010 that glacier melted away. So let's get a slightly closer view of that. When that happened, it actually disrupted air travel across the North Atlantic, throughout Europe. It's a stratovolcano deep beneath the ice here, and it spewed volcanic ash high into the stratosphere. All right, so we're coming in over the glacier now that's sitting there, so things are pretty safe. But like I said, it can get quite active as well. And that's just one of the many volcanoes over that hotspot and that Mid-Atlantic Ridge as well. All right. Well, I think we have time to go to a couple more hotspots on Earth. Where do you want to go next?
Let's go to Hawaii.
Okay. All right, so we're going to head back out into space. We're over the Atlantic Ocean right now. So I'm going to spin the globe over to the Pacific Ocean. Make sure we have some sunshine to our backs as we explore the Pacific. All right. Now, as we settle in around the Pacific, I wanted to stop for a moment and talk about some of the different ways that volcanoes form. We've been kind of hinting that a little bit. Last week we talked about the Pacific Ring of Fire. I'm highlighting that again. That's where we see lots of earthquake activity, lots of volcanoes as that Pacific plate bumps into other plates around it. But Hawaii obviously isn't on the Ring of Fire. It's right in the middle of the Pacific Ocean. So you don't need to be at the boundary of tectonic plates for a volcano to occur. Hawaii is right on top of another massive hotspot. And we're going to go in for a closer look. We're going to head to the Big Island of Hawaii, which has actually been built up by 5 major volcanoes. Now, these are known as shield volcanoes. They're shaped like a warrior shield. They're kind of broad, horizontal, flat domes, low to the ground, compared to the classic view of a cone volcano, what we call a stratovolcano. This one is known as Mauna Kea. It's the mountain of the deity Wakea, and what you can see all over are the sort of orange bumps. Those are cinder cones. So where the lava blasted out, it fell down to the ground and quickly cooled and formed those marks across the surface of the mountain. Now, Mauna Kea is actually a great place to do astronomy. There are 13 telescopes here, funded by countries from around the world. It's also thought to resemble the surface of Mars, so NASA has programs where folks can spend up to 12 months here in Mars simulation missions. If you want to be a Marstronaut, probably one of the best places you can go on Earth is to do some training on Mauna Kea. We're going to head a little bit farther south, popping back out for a view of the Big Island, Hawaii. And this time I'm going to zoom in just south of Mauna Kea to the long mountain, Mauna Loa. It's the largest shield volcano on Earth. And it doesn't explode. It actually effuses lava out of it. You can see on the screen right now where that lava's cooled down. It burns and melts whatever it touches, but usually people can outrun the lava. It's diffusing out. And it was created, like all the volcanoes on Hawaii, as the Pacific tectonic plate was moving over that hot spot in Earth's underlying mantle, the Hawaiian hotspot. One more spot I'd like to go, and that's just to the southeast here of Mauna Loa. It's Kilauea. Now, this volcano is erupting right now. It's active. It's on the southern edge of the Big Island. It's spewing lava, golden strings of volcanic glass. It was thought to be a satellite of Mauna Loa for a long time, but now we know it to be its own separate volcano. It's got its own magma plumbing system extending deep down into the earth. And it's believed to be the home of Pele, the Hawaiian volcano goddess. I'm going to pull back now for another view of the Big Island of Hawaii. So you can see here, geology is kind of a way of looking back in time. And as the Pacific plate has moved over the mantle plume, different volcanoes have popped up through the oceans and they formed this island chain over time. So as the tectonic plate was on the move over this hotspot, we saw lots of different volcanoes form this island chain. Now things are a little bit different though at our next stop. We're going to leave Earth behind and head off to one of our planetary neighbors. I am done with Earth, awesome as it is. You get to pick a planet. Where do you want to go?
Mars is the best place for volcanoes.
Always. So here we go. All right. We got a little scorched by the sun there, but we're almost we're almost there. Okay, we are coming up on the planet Mars. From here, you can see the darker areas. That's basaltic rock. But Mars is covered in rust. It's rusty, crusty, and dusty. And that's due to iron oxide. Okay, the side we're most interested right now that's got these tremendous volcanoes is actually away from the sun right at this moment, out in the cosmos. So I'm going to move the sun once more so that we can get a great look at these volcanoes. There we go. All right, so I just zoomed into a region that we can take a look at here. I'm going to pull back, though, for a planetary view. These volcanoes are so big that we actually, I think, need to see the whole planet for comparison there, because you can actually see these volcanoes from space.
Yeah, the Tharsis region is the largest volcanic region on Mars, and it has absolutely massive volcanoes, even compared to Earth's. Its volcanoes are 10 to 100 times the size of Earth's volcanoes. One volcano, Arsia Mons, is the is high. You'll hear us say Mons a lot over the next few minutes, and that is because Mons is the Latin word for mountain. Our second volcano in the Tharsis region is Pavonis Mons, and it is located in the middle between Ascarius and Arsia, and its caldera is approximately 5 kilometers deep. And though it is the smallest of the three volcanoes, it is still 375 kilometers wide. All three of these volcanoes are shield volcanoes, and the slope of Pavonis Mons is about 4 degrees, so it's not much, but it goes on for a long time. It has time to get high up in the air. The northernmost and largest volcano in the Tharsis region is Ascarius Mons, which is around 460 kilometers wide and 19 kilometers tall.
So while these are far bigger than anything you'll find on Earth, they are still basically shield volcanoes, like in principle, like what we saw in Hawaii. But they are far more massive because the tectonic plates aren't moving. We don't have that happening. On Earth, the hot spot remains stationary. The crustal plates are moving over them, and so we get those island chains like Hawaii, chains of volcanoes. But here, mountains can just keep building up and building up over millions of years over that hot spot and just turn into these massive monuments. And we've got one more to check out. So the Tharsis region is impressive, I'll give you that, but not as impressive as our next stop. This is the largest planetary mountain in the entire solar system. This is our grand finale today. If you trace the mountain on your screen right now, if you trace it with your finger, that mountain would nearly cover the entire nation of France. This mountain is 16 miles high. 16 miles. Twice as tall as Mount Everest. This is the Martian Mount Olympus. Gavin, as you said, Mons is just another way to say mountain. This is Olympus Mons. But the Martian counterpart to, on Earth, Mount Olympus in Greece, the home of the Greek and Roman gods of old. So Olympus Mons is another massive shield volcano that formed over a hotspot, a stationary hotspot over hundreds of millions of years into that towering shape. It's so vast that it actually just blends into the curve of the planet, and you can see it from space. That is the power of hotspots. So we hope you enjoyed another tour of space volcanoes. Tune in again. We'll be back next week with a whole different kind of volcano. And thank you very much, Gavin, for joining us today. Great job.
Thanks for having me.
Yeah, and if you have any more questions, feel free to drop them in the chat, or come on down and see our Space Volcanoes show on site at Buhl Planetarium, Volcanoes in the Rangos Theater, and step back in time to Pompeii, the exhibition, and learn about Mount Vesuvius and the culture that's been preserved for centuries under volcanic ash that gives us a window back into life in ancient Rome. But thanks for joining us. Keep looking up out in the night sky, and if you do spot Mars anytime in the near future, just consider that is a world of now dormant but incredibly impressive space volcanoes that formed over hotspots. All right, thanks a lot. Have a great day, everybody. Take care.